All right, in this tutorial video, I'm going to show you a little bit about how to use TerrSet to compare NDVI images. This is called a time series or a pairwise comparison to understand change in NDVI values over time. So our two NDVI images. Now, if you double click on them to open them, it's going to display a little weird. It's not going to use the correct color palette. So remember when we do this, use the display launcher. You're going to select your NDVI image from the pick list, click OK, and make sure that NDVI palette file is selected. You know that you've got the right NDVI palette file if the high values, right, up to 0.99, those are green, and the low values, reaching, almost to -1, those are the reds. So you've got your two NDVI images from February and from May, and now you need to find out, was there any change in the landscape, from one month to the other month, from February into May. So when we do this, we've got to consider a few things. One is, well, of course, it's a living landscape, right? This is vegetation. So of course, things are going to grow. They're going to grow big. They might get sick. They might die. Things are going to change, right? There's the regular variation in that landscape. That's okay, right? Or that's kind of the normal, life cycle and that sort of thing. So what we're looking at is there anything that's really out of the ordinary? So the scientific term for that would be, are there any anomalies? So are there any anomalies in NDVI change values that might, be serious, or we might need to look at? So we're going to use two tools. One is called image differencing. The other one is called area. So you open the image differencing tool. It's called IMAGEDIFF, which you can type into the tool search box. And you've got an earlier image and a later image. That earlier image is going to be the earlier one, right? That's the one from February. The later image is going to be the one from May. Output file name, you should put in something that's relevant, that's good for you to understand and to remember what's going to be saved here. You've got two checkboxes here for use mask, and you've got to use masks here because look at our files here. We've got a lot of clouds here in both images. We have ocean here in both images. And if we include the ocean and those clouds here in our analysis, then it's going to really introduce a lot of errors into our statistics that we need to do. We've got to rely on some statistics in order to find out, are there any errors that actually significantly increased or decreased outside of that normal range? And if we include all of those other values, that's too many other variables that are going to influence the statistics in a way that really we don't need it to be doing. So I've got two study area layers here that you're going to use for those masks. The masks are going to cut out those clouds and those oceans, actually kind of cuts out the study area that you want to look at. So that's how we think of that mask is. That mask layer is going to tell the software only look at this area when you're doing the analysis. So some background for that is I went ahead and created this for you just to save you some time. But if you want to do this on your own, or if at any point you need to do this on your own, here's how to do it. Is you first have to digitize a vector file where you trace a polygon or multiple feature polygons of the places that you actually want to look at. You can also set this up as for the polygons to exclude places that you want to look at. Just kind of depends on how you want to set that up. So you set up the polygons here, and you see here that I've traced this area, and it includes no places with clouds, and it includes no ocean. This is the populated area of the island that we can actually get access to through our data. That study area right here, that is specific to this layer. The other layer has its own study area mask because the clouds are different in that picture. And then from that vector file, this gets converted into a raster image, and that raster image is used as the mask. So you're going to load the raster-based mask for this for the image differencing. So when you do the image differencing, you're going to put the mask here for the earlier image and for the later image. You've got to put in the right dates. All right, and then let's take a look here. our output options. We've got a few different options here. The difference image is what's used by default. I'm going to show you what this is. This is basically just subtracting each pixel of the earlier image from that corresponding pixel in the later image, and then only in those places where the two masks overlap. So it's only where there's overlapping areas between the two masks. And of course, if we look at this, you don't need to do this for your assignment. You could if you want to, but you don't have to. When we look at this, we get this yellow background because the yellows are all zeros because those have all been clipped out. And if this might be a little confusing to look at. So one thing you can do is there is an island boundary in your files called Ambae UTM. So if you add through your composer window, add a layer, use the Ambae UTM, change the symbol file to outline black. It's going to show the border of the island here. And we can then zoom into the study area and we can look at, maybe we see a little bit of patterns here, but all of this shows us is that absolute difference from one image to the next. Now, what it's not telling us is, are those changes normal, or is that to be expected? Is this average? So we need to do one more step here, and we can use that. We can do that with the image differencing tool. So this means when you set up your image differencing tool, you're going to put your earlier and later images, your earlier mask, your later image mask, and then in the output options, you're going to click down here on standardized class image. All right, so a little bit about what this does is it's going to run a histogram on your layers, and it's going to look at the average, right? So it's going to look at that output file that you just saw. It's going to say, what is the average value for all of those pixels? And then we're doing some statistics to find out what's the standard deviation of that data set. So if the average value is a certain value, how many values are really outside that normal range. So in statistics, we talk about a standard deviation as containing, around 60%, 66% of all the data in that data set. And then 2 standard deviations containing a much larger percent. And then, 3 standard deviations contains, 90% of all the data. So, if anything is outside of 2 standard deviations, so greater than 2 standard deviations or less than -2 standard deviations, then we know that that's really out of the ordinary, right? That's not anything at close to the average change within our study area. When we click OK, we get an entirely new file that is much easier to interpret and much easier to see. So we get none of that background data anymore, and you can zoom in. If you want to add that Ambae UTM vector layer, that's cool. That can be a useful thing to do. So if we zoom in, then we start to visually identify some spatial patterns here. And of course, just remember that, why don't we see some of these parts here in our study area? That's because this is where there were clouds, and we needed to mask those out because those interfere and they don't give us good data. So our legend here, it says less than -2 standard deviations, between -2 and -1, between -1 and the mean, and then so on, and those same intervals up to greater than positive or greater than 2 standard deviations. So if you see anything that's less than 2 standard deviations, that means that's a really major decrease in the NDVI values. So we can interpret that as being, this was a big decrease in vegetation from February to May. And you can click in TerrSet, if you click that in the legend, it'll highlight those in the map. So it's a temporary visual. That's kind of a cool thing. It doesn't give you a permanent, but it gives you a quick visual on where those patterns might be. If you look at the darkest green, that's areas where it was greater than 2 standard deviations. So these are areas where there was actually a pretty significant increase in vegetation from February into May. The rest of the area, which you'll see that is a lot of the study area, these are right around the average. So these are places where, there might have been a very small increase or decrease, but this is within the average. This is what we would expect there to be under normal circumstances, right? So we're interested in those anomalies, the big decreases and the big increases. For this assignment, you just have to look at the decreases. That's what we're going to be doing. We want to find out, how much area it was there that decreased by more than 2 standard deviations. So that means we need to find out how much area is classified in this standardized class difference image as less than -2. So we can click here, we can see that, but how do we actually find out the numbers, right? Well, so we'll get to that in a second. So one thing that we do want to try to do, and you can write this in your homework submission, is one thing is to just visually scan this image and to find out, are there any spatial patterns that are just evident to your eyes now that we have our statistics? And we can see that by looking at, so please take a look at this and try to see, are there any spatial patterns? Remembering that here along the coastline, northwest here, that's the ocean. So as it's going up, this is farther up the mountain. And so, are there any differences at lower elevations versus more inland or north? Are there any trends from north to south, so on and so forth like that? So try to look for any visual patterns that you might see. All right, as far as within the whole data set, let's calculate how much area has been affected. So for that, we're going to use the area tool. After typing in area into the toolbox search bar, or you can go through the menus to get to area, you're going to get the tool here. That's the calculate areas, and you're going to switch this to the tabular option here. We don't need to make a new image. We just need a table to tell us how many hectares are there under each category. So our input image is going to be the image file that you just created. And you have to remember that you need to have created the standardized class image that you just saw, where it shows less than -2 standard deviations. Now we want to find out how many hectares there are. So change this, calculate area, change that to hectares, and you click OK. And then we get a table of data. Now, how do we interpret this data? How do we understand this table? So we've got a category, we have a number of hectares, and then we have the legend. So the category, that refers to the value or the attribute that's in each pixel. So of course, in a raster data format, each cell just gets a number associated with it. And so, but we can also attach a legend to that. So when you run this tool, and I'm not going to do it here because that'll just show you the answer. But when you click OK, you're going to get a table of information, and you want to see, how many hectares are there associated with those cells or those pixels that are less than -2 standard deviations. So how many hectares were greatly decreased across our whole study area? And you're going to go in to your title, into your map properties when you do this. And quick reminder of how you do this is you've got your map in your composer window. You go into map properties right there, and you go into the title tab. You're going to write your title. That's where it's going to have your name, put the title of the map. And then for the subtitle, I want you to put in how many hectares there were that are less than 2 standard deviations of NDVI change. And that's how we use the image differencing tool and the area tool to calculate how much area has been significantly changed from one period of time to another.